In this problem, we need to design a box. We know that we have a set volume of 2197 cubic inches that we need to have, but we want to minimize the surface area so we can cut costs. So first of all, if you're looking at this box, let's say we have x, y, and z. Those are the dimensions of our box. We know that our volume is supposed to be 2197. And usually volume for a rectangular prism, a rectangular box like this, would be x times y times z. So let's write this down. This would be our constraint equation. Just like when we did this with fewer variables, you're going to have a constraint equation and an objective equation. Okay, then we're going to look at our surface area, which I'm just going to call A. We want to minimize that. Okay, well, how would you find the surface area? What you do is you find the area of each of these, well, surfaces. So this block right here would be an x, and this height right here, I didn't write this way, but it's a z. So we're going to have x times z. And there's another one just like it here at the back. So let's say there's two of those. Then I need this block right here. Well, that's a y times z, and there's also one of those in the back. So let's do 2yz. And the top looks like it's going to be an xy, and there's also one on the bottom, so 2xy. And this is our objective equation, what we want to minimize. Now the problem here is that we have three variables, x, y, and z, and we only know how to find a minimum or max for two variables. So what we're going to do is we'll use this constraint equation up here to solve for one of those variables, and then we'll plug it in down here so we can get rid of one of our variables and be down to just two. So let's see, so let's do 2197 equals x, y, and z. And let's solve for z. You can pick anything to solve for, but I'll just solve for z because it's my least favorite, so I can get rid of it. So let's see, then z is going to equal 2197 divided by xy. And now let's plug this into our surface area equation. So we're going to have our area equals 2 times x times, instead of a z, now we'll put 2197 over xy. Let's see, so we have 2197 over xy for z. Okay, now plus 2 times y times z, which again is 2197 over xy, plus 2xy. Now at this point, luckily this simplifies, so it's not as bad as it looks because we have an x over an x and a y over a y. So let's bring those out. So a is going to equal, let's see, 2 times 2197 is 4394. The x's cancel. Oh, but we still have over y. Let's change that. I like to write these as y to the negative 1. It makes it easier for me to do derivatives. Plus now again 4394. And we'll say this is times x to the negative 1 plus 2x times y. So now we have a, which is down to just two variables, and you can use all of your other tricks from all the other problems in the section, and you just have to optimize it. You need to find, in this case, the minimum. So when we're finding our minimums, we'll take each partial derivative. So let's do the partial derivative of a with respect to x. So in this case, we only care about x's, so like this term just has a y, so that'll just be 0. And then we'll have 4394. Let's see, x to the negative 1, that means we'll bring down the negative 1. Then you'll take your x and you'll drop the power by 1, which means to the power of negative 2. Plus, and 2xy, the 2's there, the derivative of x is 1, and the y stays there like any other constant, just like the 2 did. So this is 2y minus 4394 over x squared. Now usually we want to set this equal to 0 and solve. But the problem is we still have an x and a y. So what we'll do is let's go ahead and find our partial derivative with respect to y. Now, so it's going to be pretty similar. This derivative with respect to y, using our same logic, is going to be negative 4394 over y squared. Plus this x, this just has an x, so we don't care about that. And then the 2x is a constant, derivative of y is just 1. So we get 2x minus 4394 over y squared. And we need to take this, set to 0, and solve. So basically now we have a system of equations that we have 2y minus 4394 over x squared equals 0, and 2x minus 4394 over y squared equals 0. There's different ways you can solve systems of equations. You can do elimination or substitution. This one would probably be easier with substitution. So for substitution, what we'll do is we'll come here and let's solve this one for y. So we get 2y equals 4394 over x squared, or y equals, let's see, 2197 over x squared. And then we'll plug in and over here. So we'll have 2x minus 4394 over y squared, but y is really 2197 over x squared. So we need to square all of that equals to 0. And solve for x. So as you can tell, this is starting to become quite a complicated problem here. Let's see, so we have 2x minus, this is a 4394. Now we're dividing by a fraction. So instead of dividing by a fraction, you can flip it upside down and multiply. And we'll go ahead and square. So this is going to be x to the 4th over 2197 squared equals 0. So we get 2x minus 2 over 2197 x to the 4th equals 0. Let's see, at this point let's factor, because we're in solve for x. So we have x times 2 minus 2 over 2197 x cubed equals 0. So you set each part equal to 0. So x equals 0, or 2 minus 2 over 2197 x cubed equals 0. And let's go ahead and rearrange this. So x cubed equals 2197. And if you take the cubed root, which equals 13. Okay. Now as you look at these, can x be 0? Does it make any sense to make a box that has a 0 as any dimension? No. So the only logical one would be this x equals 13. Now that we know one dimension, which this problem is taking a lot longer than you might think when you first look at it, now solve for y by plugging this in somewhere. Let's go back up to our last equation that had a y right here. That one looks good. Y equals 2197 over x squared. So y equals 2197 over x squared. So 2197 over 13 squared gives me 13. So we have a possible minimum at x equals 13 and y equals 13. Now, technically, you should go through and calculate your d of x, y, and to see if it truly is a max or min, because it could be a saddle point. But on story problems, usually we find that the only number that comes out as an option is probably the one that is a true minimum. And so at this point you probably spend enough time that you probably skip it. But if you want to, you could go ahead and calculate d to make sure it truly is a minimum. But if you look at your view, your example, they'll go through the work for you and you can see that, let's see, d is equal to 14, which is positive. So it equals 13, and the second partial of s with respect to x is greater than 0, so it is a minimum. So you can check that on your own time. And the last step is we're supposed to find all the dimensions of the box, so let's find z. And to do this, we come way back up to the very beginning to our last equation that had a z in it. Z equals 2197 over xy. So it equals 2197 over x times y. So 2197 over 13 times 13, which equals 13. So to minimize surface area, make the box 13 by 13 by 13 inches. Which makes sense because we find that if you're doing just like a plain box with no missing tops or anything, you always get the best volume for your surface area if you do a cube.